minute to get up and running, so I'll start the class in just a minute from now. But you, yeah, so let's get started, everyone. So welcome back. We're going to start today by, I have a short guest presentation by Vanessa Ambergy. So she is representing, I forget the name, the CSSI, I think. So it's a center on campus that is collecting and making available a bunch, or CTSI, that makes available a bunch of data having to do with like the clinical side of the medical domain. And so I know you're all working on projects, and a number of you are working on things related to medical data. And if the data she is describing seems very interesting, then this would be kind of, it's not too late to kind of reconfigure your project to try and do that. But if you're not doing that, I hope this is still interesting. Just being aware of some of the resources available on campus to provide access to these things. So I will give the floor to Vanessa for a few minutes now, 5 or 10 minutes.
Yeah, thank you so much for having me on. I appreciate coming into your classroom. And hopefully I can help if you are still in the process of looking for data or a data source for your project. I am going to go through some of this stuff pretty quickly, but I'll have my contact information at the end, and do reach out to me if you want to have a longer conversation about any of this. It's actually my job to help researchers connect to data. So if you're looking for something to do a project on, or you want to know more about anything that I mentioned here, just let me know and I can help you with some of those resources. So just a brief overview. The majority of the data that I work with is stored in electronic health networks. And so this is the system that your doctors and providers use to store information about you and your health. It comes often from different networks, all together harmonized, and they take the personalized and personalized identity information out to make those data sets de-identified and shareable. And some of this information goes on to help with pharmaceutical companies, all of the things that you would expect to happen with health data, but researchers at the University of Utah can also access this really for a wide range of research needs. And so I can help facilitate those connections as well. At the University of Utah, we have a handful of research data networks that we consider our primary networks. There's varying types of access depending on what your project is like, and the time to get a hold of the actual data can vary a little bit. So if you're interested in getting into any of these networks for raw data, it can be a little bit of an involved process, and it's tricky to do in a single semester. But if you have a longer term project, or if you are connected to someone who has already gone through the process and archived some of this data, then we can help you get into data that way. Several of these have interfaces that if you wanted to run queries or analysis on them and look at the aggregated data, that can happen very, very quickly. So depending on what it is your need, and what it is that you're trying to answer. Some of these can be really useful for that purpose. Just to give you a sense of what is in these data sets, we'll take a look at Trinetics, which is one that we use commonly, and we can get aggregate query data from this very, very quickly. It has demographic information, diagnoses, medical procedures, labs. There's a lot of granular data here. And if you are interested in moving forward with the work that you're setting up or proposing in this class, we can talk about getting you a larger data set. And so you can look at actually individual line level data sets that contain this information. But that is a slightly longer process. So knowing that your turnaround for your project might be a little quicker than that, I've pulled up a handful of additional resources here that I thought might be useful. Some of these are actual libraries. So like the Re3 data, which is the second line down there in the table, that is a repository of different types of data sets. And these are free data sets that you can download the data today. You don't need to set up an account for them. They're depending on what you're interested in, the type of information that you need for the project that you're putting together, that you may be able to find a data set that could be really useful in a project like in one of these. And I'm happy to talk through any of these in more detail. I only just have a few minutes with you here in your class today, but the website for the CTSI is over there on the left-hand side of the page. And I'm going to, again, put up in just a second here, I'm going to put my own details up, and I can pass these slides along to Jeff so that he can put them out as well. But just to give you kind of a sense that we do primarily work with electronic health research data, but really I am putting together a catalog of all different types of data sources and even libraries of data sources. So if you're looking for something, if you want to even just throw some ideas around and have somebody else respond to those and talk through them with a person, I'm happy to do that as well. That's part of the work I do. So this is me, and here's an email address where you can reach me. And if you are within the U system, you can find me there as well. And I'm sure Jeff could put you in contact with me as well if you wanted to give out my email. I'd be happy to field emails or have conversations or do really anything to support your projects. So that was a really quick run through of what we can do. Are there any questions that have come up, or is there anyone?
Oh, any quick questions? Yeah.
Do you guys also have like a psychological?
Do you have so a report about psychological data? Do you have any data sets that touch on?
There are. So let's see, let me go back a slide. I know that there is some mental health related data in the Utah Open Data Catalog that's at the bottom line here. I have offhand another national source that can point you to data sets around national mental health screenings. A lot of times data sets that have to do with mental health and psychology are looking at the prevalence of different types of health and psychology scales. So if you have a particular scale that you're interested in, sometimes it's a little easier to find data associated with that. But yeah, send me an email and we can go back and forth a little bit and I can help you look.
Yes, great. So thank you. So thanks for coming by. And if you're still looking or for this project or for the next project you're going to do, this is a great resource. I encourage you to reach out to Vanessa and the CTSI. So great. So thanks.
Yeah, thank you.
Yeah. Okay, let's see if I can share now. and stuff I'm worried about. Works. So great. So okay. So again, the data collection report is due on Wednesday. So a week from now. So again, you should be kind of, remember, we went over the last lecture, what the steps are. You should be looking in there, try and simulate the data. There's lots of kind of yeah. So again, if you are at this point and you realize that you don't think the data set is going to be good for what you want to do with it, or you see that from the feedback we get from looking at your data collection report, you should come and talk to me, and I can help you navigate where to find some interesting data if you haven't yet at this point. Okay, so a couple other administrative things. I had warned yesterday or on Monday that I probably need to cancel my office hours tomorrow. I just found out that they're uncanceled because unfortunately, the National Science Foundation panel I was going to be on has been canceled or postponed. I just found out like 10, 15 minutes ago. So it's been interesting times in the world of research the last few weeks. Okay, and we'll see what happens. And then let's see. And then the LSH homework should have just been due. So hopefully that's gone well. We will post hopefully the clustering homework sometime soon. We're finalizing the data sets we'll give you for that. Okay, anything else? Okay. All right, so let's get into the lecture. We're shifting topics. We kind of are getting out of a long, kind of an expanded, and maybe after we went through it, it felt like a little bit longer than I wanted section on notions of distance and similarity and how to find things which are similar. We're moving into clustering part of the semester. I'm hoping that you will see how integral the use of modeling distances is going to be in the rest of what we do. Okay, it's starting with clustering. Okay, and that this setup we've had, which is a bit longer than maybe I had realized, is going to kind of give us a foundation. So we'll cover a few things in clustering, a few algorithms will be more algorithmic, but you'll see it immediately applies a huge swath of modeling depending on how you choose to kind of include one distance or another. Here. Okay, so we're going to start. We're going to talk basically about there are a huge number of types of clusterings. There are hundreds of papers a year on someone says, aha, this is the right way to cluster. And that we're going to talk mainly about three categories of them in this class. The first one will be hierarchical agglomerative clustering, and I have agglomerated density-based clustering in this lecture. Okay, so we're going to include density-based clustering, which is kind of a cousin or you can think of it as a more efficient version of the hierarchical agglomerative clustering. Then next lecture on next week, Wednesday, we'll talk about the center or assignment-based clustering. This includes k-means as the famous one in this group, but I'll tell you about some other ones in this family, which I think are just as useful as k-means. And then the third one we'll talk about is spectral clustering, which is kind of whereas hierarchical clustering, agglomerative clustering at least, will be a bottom up, where we're building clusters by growing them from very small things into big things. The spectral will end up being top down, and we'll use both thinking about things as a graph and also using matrices and linear algebra a little bit. So we're going to kind of start getting into that sort of territory with that. Okay, so let me start with what is clustering. Clustering. Okay. And so well, I'll be clear, I've worked in some spatial data analysis as well. And in spatial data analysis, when they say clustering, they mean something else. They mean like what I would call spatial anomaly detection. But in our context, what will clustering? Well, it's going to start with some input, and the input is going to consist of two things. The first one is a data set X. Okay, we'll think of this as objects X1, X2, up to Xn. Okay, and a notion of of distance. So if these are in some space, that's a script X. It looks totally different than uppercase X, right? Okay. Hopefully you can tell the difference. So the distance will go between two things in this space. Okay, there are lots of X's, different types of X's on the screen right now, I realize. Okay, but it'll give a real number, and the distance will go between two things in the set. I need to measure a distance between them. Okay, your input is important to understand. Your input consists of these two things, not just the data set, but you need to prescribe the distance as well. It's often implied, it's often, but not always the case, often that X is a subset of RD, and that our distance between X1 and X2 is just going to be the Euclidean distance. Okay, so this is often the case, but this is not always true. The examples I will probably give and try and illustrate with will probably be points in two dimensions. And this sometimes illustrates what's going on well, and it sometimes does not. Okay, sometimes I can replace any distance as long as it's a metric. Sometimes it can be any notion of distance. It doesn't really matter. Other times the algorithms only work with Euclidean distances or things that work close enough to Euclidean distance, such as the kernel distance or the angular distance. It turns out you can mostly get to work with these methods as well. Okay, so, but the notion of distance is part of the input of the problem. Okay, and if you give data and you don't have a good way to measure distance with it, your clustering is going to be just kind of a mess. Okay, so back to the formulation. This distance X, I'm going to think of as some points, and now I'm drawing them on the screen. That means I'm thinking that we're in R2, and I'll think of the Euclidean distance for this example. And the goal is to partition X into some K sets, S1, S2, up to Sk. So think of here, this might be S1, S2, S3. Okay, and in fact, I've just run my favorite clustering algorithm. Okay, my favorite clustering algorithm only works in two dimensions pretty much. What I do is I take the data, I plot it in two dimensions, I take out my pen, and I draw circles around the groups of points. Okay, this is my recommended clustering algorithm if your data is in two dimensions. I'm not kidding about that. Okay. Okay. Well, I'll explain over the next few lectures why I'm serious about that. But okay, I haven't told you to partition into sets. I need some more properties about this. Okay, so these sets, what makes a good set versus not a good set? Okay, I'm going to have two things I want to occur. One, I want, and this partition has two properties. It means that S1 or Si intersect Sj is the empty set. So these sets are disjoint, and that the union of j equals 1 to k of Sj is going to equal the whole set X. So it's partitioning. Each point is in exactly one cluster, and the clusters, no point is in multiple clusters. Okay, this would sometimes be called a hard clustering. This is kind of, there's a soft clustering where points can overlap, and I don't think we'll talk too much about that in this class, but okay. So what makes a good clustering? So I have two goals part of here. I want points in cluster. So x1, x2 in Sj, I want these to be close. So d of x1, x2, I want to be small. Okay, so if I take 2 points, oh, why did it do that? Okay. So x1, x2, I want this distance between them to be small. Okay, if they're in the same cluster, they should be close to each other, should be similar, their distance should be small. Second, I want points in different clusters. x1 in S1, x2 in S2 should have the distance between x1, x2 large. Okay, so if I look at x1 prime and x2 prime, right, these are two different points in different clusters. I want this to be large, and I want this one to be small. Okay, so points in the same cluster, they should be close to each other. Points in faraway clusters should be far away from each other, or in different clusters should be far away from each other. Okay, this is kind of the general notion of what clustering is. And I've tried to keep it pretty generic here in general, because there are lots of formulations of this, and a lot of people will swear by one clustering formulation is, or algorithm is better than the other one, but they're all basically trying to do this. Okay, and again, my favorite algorithm if data is in 2 dimensions is to plot it on a piece of paper and to kind of try and draw circles around tightly grouped sets of points that are separated from each other. And if you can do this, then you should feel good that this is a good cluster. Okay. We'll talk about some other algorithms that you can write on a computer, but like you kind of don't know to trust what these mean so much unless you plot them. We'll talk about some other kind of strategies as well, but they're kind of, nothing is as satisfying as this if you can do it, right? Sometimes you might, in your homework, you're asked to run clustering algorithms, and I've given you 2 of the data sets will be in 2 dimensions, and I'll ask you to run specific algorithms, not this one, but you should plot them, and then you can color code the points so you can kind of see what's going on. That'd be kind of another way, but you know, on the board it's easier to, or on the iPad easier to draw circles around. Okay, we could stop here, and I would be mostly satisfied, but let's talk about some other algorithms here. Okay, before we do that, this is kind of my feelings on clustering. When data is easily or naturally clusterable, whatever this means, then most clustering algorithms work quickly and well. Okay, when data is not easily or naturally clusterable, then no algorithm will find good clusterings of the data. Okay, so if the data looked like I showed on the previous slide, that was the first category. It didn't matter so much what algorithm I used, they should all pretty much give the kind of the same answer. When data is not naturally clusterable, then no algorithm is really going to work, or is going to be able to find you clusters. Kind of a common example that people get when plotting is they'll get data in 2 dimensions, and a lot of times the data kind of looks like this. And you know, from doing this class for many years, I've seen many people try and run clustering algorithms, and the data will look like this, and they say, I'm going to run clustering on it. And then they run some algorithm and it picks this cluster and this cluster here, and maybe this one, and then everything else is in this cluster. And they say, I'm done. I ran clustering on this algorithm. I like to call this kind of a smear. There's a piece of cream cheese and you kind of spread it out with your knife. And say, now I want to cluster the cream cheese, right? There aren't any really good clusters here. There's nothing you can do, at least if Euclidean distance is your notion of distance here, that you're going to be able to do good, find well-grouped clusters that are themselves close to each other, and the clusters are far away from everything else, right? You can kind of do that here by partitioning the point sets, but I don't think that's really helpful. Okay, I don't think it's really gaining you anything by just partitioning them like this. I've seen plenty of fancy presentations where people claim, oh, look at the clusters we found here, but I'm not convinced. Okay, I don't think there are any good clusters in this data set, or there's one cluster. Okay, it's not too interesting to me. Now, it could be that there's a very different notion of distance, right? I somehow have data and I'm looking at two parameters of the data and I'm plotting it this way and I get the structure. But if I somehow relook at the data and come up with a very different way of measuring distances between things. For instance, there's this like million song data set that is one of the data sets I think I probably linked to, if not directly, indirectly, in the project report. And the most common way of plotting it looks kind of like this. Yet people come up with pretty good clusterings of songs into different groups of types of music, right? That there's classical music versus pop music versus rap versus country versus whatever you young people are listening to nowadays. So there's some way to do a cluster of the music, but it's not this, right? There's some other notion of distance between the songs that must make sense, right? And so you have to come up with the right distance in order to find useful clustering of these songs. Yeah, yes. Okay. Another common thing. So why am I telling you 3 different classes of clustering algorithms? And we're spending 3 lectures of the class on this. Well, it's a data mining class. It's kind of a natural topic in data mining. What happens is the different algorithms specialize in some fairly nuanced differences between the types of data. The sort of algorithm we'll talk about today will work well with these kind of like these 2 moon sort of data sets that look sort of like this. And if you look in a bunch of papers in data mining and clustering, they'll draw data that looks like this, where there's meant for there to be one cluster here, and there's another cluster like this. And you want to be able to find these 2 different clusters of the data. And so the hierarchical agglomerative and the at least the single link version we'll talk about, and the density based will specialize in finding these sorts of clusters. I have seen data sets where this was the right thing to do, but very rarely, and I've looked hard. Okay, this example is one you can generate. It might even be built into Python where they can generate data automatically that looks like this. But like in general, I don't know, if you see data that looks kind of like this and you think it actually came from real source, I'd be interested to know, just for my own kind of sanity if this happens, but I don't think it happens that much. But we'll talk about these hierarchical agglomerative and density-based clustering because they are quite commonly used and you should know about them. Okay, there are a couple other things that they can be useful for, and we'll talk about that. Okay. Okay. So this hierarchical agglomerative. Hopefully, I won't have to write this anymore after this time, HAC. Okay, so kind of the clustering, this clustering is kind of a little bit unsatisfying from my perspective in that it is basically described by a procedure as opposed to what you would like to get out of the cluster. Okay, it's like, I'm going to tell you a procedure and the output of the procedure is the definition of what the clustering is, which is kind of from someone who comes from a bit more of a mathematical background, kind of frustrating because I don't know what that means. So let me, well, people have analyzed it and stuff, but this is how you should think about it. Okay, and the idea is that you're going to have some data set. Okay, this is my input. And again, I'm drawing pictures with some examples in 2 dimensions in Euclidean distance. And I'm going to start where the first step, okay, is that each x in X is its own is going to be its own cluster. So S1 is going to be the set x1. S2 is going to be the set which just contains x2. Okay, and then so and so on. Okay, and then I'm going to gradually from the bottom up merge the clusters together. I'm going to agglomerate. I don't know what the form of that verb is, but I'm going to kind of combine together these clusters. And the basic idea is I'm going to, at the first level, when they're all points, I just need to find the 2 points which are closest to each other and merge them together into a cluster. Okay. So basically I'm going to have a while loop. Okay. While that there are while more than one kind of cluster. Okay. I'm going to find the 2 closest clusters, Sj and Sj prime, and I'm going to combine into Sj equals Sj union Sj prime. Okay, so I've taken 2 points, they were each 1-point cluster, and I've combined them together into one cluster now that has 2 points into it. Okay, so I'm going to find these two clusters. Yeah, and actually, yeah, I wrote 2 steps in one here. So let me I'm going to merge Sj prime into one cluster, Sj union Sj. Okay, so this is the whole algorithm. Okay, so I'm finding the 2 closest clusters, and then I merge them together. Okay, so maybe the next 2 points are here, so I'm merging these together. Then I say maybe these 2 points are next, and then maybe I decide this point merges with this cluster. So this becomes one cluster. Here, this merges into a cluster. Maybe this merges into a cluster. Okay, and it's starting to get a little bit messy here. Eventually, everything merges together into one big cluster. Okay, and so what's happened is I've kind of eventually I merged everything into one cluster. Okay, so great. Why was this kind of so helpful? And so you can think of this in parallel. You have a hierarchy. Let me draw a smaller example. A, B, kind of C, and D, and a point E here. So I can write A, B, C, D, E. And so I first merge A and B, then I merge C and so these together, then C and D, then maybe I merge these two together, and then E merges everything together in the last step. Okay, in this smaller example, I'm building this hierarchy like it's a binary hierarchy, but I only merge two things together at once. And so I have this like this tree you see of like so phenotypes of different species. You kind of a lot of work in biology is trying to understand the evolution of species starting from now. Then if you like, there are the kind of I guess humans, and they split off from apes or something, and then there's like the mammals and the reptiles, and then there's the plants and the animals and so forth, and there's this big phylogenetic tree, and we try and understand that from the characteristics of the species, about how similar they are, and you build it from bottom up. You build this kind of clustering of types of life, right? Okay, so kind of it gives you this hierarchical structure. And then afterwards, I can say, well, how many clusters do I want? Maybe I'm going to stop it off after. I'm going to say, I only want 3 clusters afterwards. So I will use these 3 clusters. I can decide how many clusters I want after I have, after I've run the algorithm, instead of before I've run the algorithm. Or I can go and say, well, at what point do the clusters get dense enough that I want to keep them? Okay, and if this A, B, C, D cluster, this was too big, I don't want to call that all one cluster. Let me split that, and then I'm satisfied at something. Okay, yeah.
Okay.
Yeah, okay. So great question. Kind of you added find the 2 closest clusters. Okay, how do we find, and so you asked, how do we do this efficiently? And so you're asking the right part of the question, but the efficiency is kind of a secondary point, I think, to what is the notion between 2 clusters, two sets, right? I have 2 sets, okay, of points, and I want to come the distance in between them. Okay, and now, okay, we could use one of those fancy things like the kernel distance or the Wasserstein distance between the point sets if I wanted to. That's typically not what's used here. They use something even simpler. We'll talk about a few variants of this, okay? And so we'll also talk eventually about how do we retrospectively, perhaps, or as we're running it, decide when to stop. Those are kind of 2 questions here I haven't answered. The main question, though, is what do I mean when I say find two clusters which are the closest? Then hopefully the rest of the procedure takes care of it. It's pretty straightforward. Okay, but I have to find the 2 closest clusters. Okay. Okay, let's go next slide to talk about that. Okay, so find the 2 closest clusters. Okay, and so what do I mean by this? I have okay, let's do an example where I'm at a state where I've got these 3 clusters. I'll call them S1, S2, and S3. And how do I define the distance in between two clusters, right? Now I need to define a distance, D, between, say, S1 and S2. Weird S. Okay, so how should I define this distance? I said I could use a distribution distance. So the Wasserstein or the kernel distance, but this is not the most common thing. This is kind of older idea than when these became popular. So what are other ideas about how I could tell the distance between 2 clusters here? And I'm given to you a base metric. I'm given to you this notion of D, which applies between the point sets, right? So I'm given an input where between 2 points I can measure a distance, and I'm going to use that somehow. For instance, I can use it in the Wasserstein or in the kernel distance in ways we talked about Monday. But what is an even simpler idea? Yeah. Oh, okay, great. So the distance between C1 and C2, where Cj is the center of Sj. Great. So okay, how do I define the center? Great. This could be the mean of Sj, right? That's a perfectly reasonable way to define this, the center. Right. So this would be center one, be the average of all the points. Very popular idea, and it will build into k-means clustering, which we'll talk about next week, Wednesday. Great. So this would be called, this was one way how to do it. There are other ways to define the center of a point set. For instance, I can say the center of the minimum enclosing ball. All right, so for this set of points, I can find the smallest enclosing circle and look at the center of that. That's a different answer than the mean, right? This is another valid choice. There are other choices, especially in high dimensions. How do I find a single representative point of a cluster? There's a wide variety of things I could use here. Okay, great. This is a common one. What's another idea? The two closest points, yes. So where D S1 S2 equals the min of x1 in S1, x2 in S2, the distance between x1, x2. Great. So this is called the single link method. This is a very popular one. In fact, probably the most popular version of hierarchical agglomerative clustering. And so this just looks at these two things and it finds the closest pair of points, or in this case, it would be these 2 points here, right? So it just looks at the closest pair, okay? And this will actually work really well for this 2 moons data set. These are kind of like these 2 half moons. It'll connect every point is close to another point in the clustered set, but the difference between the 2 clusters is pretty big. Okay, so this will actually, this will work. This is what works especially well on these 2 moons sorts of data sets. It will find things that have some evidence that they're connected without ever going too far from something in the set. Okay, now even if I started by building clusters kind of here and here and here and here, it says, well, there's some connection in between, so I can connect these together later. Okay, where if the center of the 2 clusters kind of starts to grow further and further apart, it becomes harder to connect them, and you might connect stuff across from the red to the purple moon if you do it using the center-based cluster. Okay, there's one other common version here I want to mention. The single link clustering has the potential downside that I don't need the full data set to be close to everything else in the full data set, right? Remember our mantra at the beginning is I wanted everything within the data set to be small and the things across the data sets to be large. And so that may not be true in this 2 moons example where 2 points, this point and this point, these are far away from each other, even though they're in the same cluster. Okay, so this is maybe, for this sort of data set, this is maybe not, if that's what I wanted, this would not give me a good outcome. What would a version of this hack clustering that could make sure I never got too far away from between two data points in the same cluster. Okay, yeah, so this is one way that I'm not going to have room to write it on the slide. This is similar to what we want. We want, and slightly different than the most common version, but I want to consider if I merge the two clusters, what would the radius of the minimum enclosing ball be, right, after I've merged them, and I can check all possible merges and see the one that gives me the smallest overall radius. This would be kind of, we will talk about another algorithm for this particular formulation that's better and easier. Next lecture. Okay, it's close to that, but I want to kind of just use it to measure a more direct distance between the clusters themselves. Okay, let me. Okay, I'm going to somehow use this distance. So instead of using the minimum, you can just use the maximum. Okay, so I just find the maximum. This is called complete link. Okay, and so it's between two clusters, it finds the 2 points which are the furthest away from each other as the distance between S1 and S2, and between S2 and S3, it's the 2 points which are furthest away from each other. And so it's using that, and the idea is then that radius tells me all the points are within that distance of each other. Those are the longest two things, so I never want points to be further than some threshold. I can actually run this algorithm until no two clusters can be merged without violating this threshold. So this would be a nice way to stop, right? And with the single link, I could run it until this distance hits some threshold, and then I can stop. And I know that within each cluster, there's some way to make small jumps that are always below some threshold. Okay, so these are the two most popular versions of this, and they give very different outcomes. The complete link will ensure the clusters are very compact, okay? And the single link will ensure that clusters are not close to each other, right? The threshold I stop at for a single link clustering, I know that the two clusters are at least separated by that amount in terms of any point from one cluster and the other cluster are never closer than that threshold when I stop. So one is basically there are these two objectives. Points in the same cluster should have a distance that's small, and points in different clusters should have a distance that's large. By optimizing the other one at this agglomerative step, this one where I ensure that the points in the same cluster distance is small, I use the complete link clustering, the complete link version, which is looking at the furthest point. And to ensure that the difference between the two clusters is large, I use this single link, just looking at the closest point. Okay, so there are these two different objectives. They have kind of these inverse ways of measuring the distance between the clusters. Okay. And the other ones kind of do something in between, right? Something about the roundness or the distance from the center, the representative point. These are also useful things to do. Okay. Let's think about the single link and complete link versions of these. Turns out like the mean one, you can run a little bit more this version where I'm thinking about the center-based distance where I'm using the mean. It turns out there's kind of a faster way to do this one. But let's talk about the runtime of HAC for, let's say, single link. Okay, so how long does the runtime take? Well, let's assume I get down to a constant number of clusters. So I might as well kind of cluster all the way to the top of the hierarchy. So so one question is how many merges do I have to do? Okay, so how many times do I have to merge clusters if with the size of x equals to n? Is it like log n, square root n? How many times do I have to merge to build a whole hierarchy? Okay, if every time I merge something, one of the clusters wins, right? So, and there's one winner left over from each cluster. And think of this now as like as a tournament where they were playing a game. How many people lose in a tournament, in a single elimination tournament? Yeah, everyone except one person loses at some point. And that's how many times I have to do one of these merges, right? So there's n minus 1, which is O of n. So merges. So I'm basically spending linear time in the merges. And okay, and then how long? So I also have to do this thing where I find the closest to find the closest two clusters. Okay, so for about half the run of this, I have still at least n over 2 clusters left, right? So I have to search all the clusters, and I have to check all the points across all kind of all the clusters. I can kind of maintain a distance between clusters I've checked before, right? So I just have to update. So I have to update. So if I merge Sj and Sj prime into Sj kind of prime, I just have to update these distances to cluster S, each cluster Si plus 1, and so forth. Right? So I only have to, so between Si and Si plus 1, their distance didn't change. I don't need to update those. So I only need to update this new merge cluster to everything else. Okay, so this will take, but this might take linear. I have linear things I need to update. I don't need to update n squared things. I only need to update n things. I can keep a priority queue in logarithmic time of the smallest distances. Okay, so I have to update. I have to merge these, and I have to update O of n, so of the distances. Okay, and then maintain in a priority queue in log n time. Okay, but computing this might take, if I'm doing single link, I only have to check the single link, the old single link of the other two clusters, right? So each update, if I do it cleverly, I can do it in constant time for each of these, right? Because the single link between a cluster Si and either Sj or Sj prime, it was the single link distance to one of those two guys before. So I just need to check that. So this I can update. So if I'm clever about this, each in O of 1 time. Okay, so this, if I'm clever, I can do n squared log n time. Okay, so this is okay. But if you have a large data set, n squared starts to get a like slightly painful. You'd rather it be linear time. Okay, so most algorithms in data analysis, if you build all distances or similarities between points, they take some, you can often get n squared. If you have to do a eigendecomposition, it's n cubed because it's more time on top of that. But you'd really like something near linear. You want things to scale really well with large data. So this might be this is considered kind of slow. I'd rather something that scales linearly with the data. Okay, so this is generally considered kind of slow. Partially because I don't need, if I'm building, right, if I started here and I drew this kind of hierarchical structure, kind of most of this was useful, but that's because I only had 5 points. When I had even 10 points over here, the hierarchy started getting messy and I probably didn't need most of it, right? And if the idea is at the end of it, I want 5 or 10 clusters out of 1,000 points, most of the hierarchy, I don't actually need that much. If I want the whole hierarchy, I probably need to spend kind of quadratic time. But if I only care about the clusters at the end, maybe I can do something faster. Okay, and this led to this idea of the density-based cluster. Okay, and this is trying to kind of approximate, and in particular, we'll talk about DBScan, which is the most common formulation of this. And this is approximately a kind of chopped off single link, like the hierarchical agglomerative cluster. So think I ran single link, but I only care about kind of the top of the hierarchy. And really, I'm given some sort of radius r, where I want clusters to be separated if the distance, the single link distance between S1 and S2 is greater than R. Okay, so think if I was running single link until I got to some threshold R, I kind of want to do something like that. Okay. The density-based clustering has another thing. It says what I don't want necessarily is if I have a data set that looks kind of like this, and another cluster over here, and then there's kind of this string of points that's kind of connecting them, and these points are kind of close to each other. But really, I've got a big group over here and a big group over here, and the string between them is not really interesting. All right, so I want to identify some notion of density, where I want to say that this region here and this region, these are dense, right? Per area, I have a lot of points, and this area here is not dense. Means that per area, if I looked at the ball, and what they mean by that is if I look at a ball of radius r, not dense means not many points, and I'll have some threshold tau. Okay, so I'm going to say, so I'm also going to have some threshold tau, which is the min number of points in ball of radius r, right? For it to count as dense. So it's dense if I look at a ball of radius r and there are at least kind of tau other points in there. Okay. Okay, so this is kind of the input to density-based clustering, and I want to use this to kind of do something like single link, but not include these little thin strands. I only want it to connect things if there's a dense region in between. Okay, so this, and I don't want to make multiple passes. I don't want to basically every time I group things together, I don't want to have to make a linear scan over all the data again. I kind of want to make 1 or 2 scans over the data and quickly determine kind of which points are connected to which points. Okay. So the algorithm is first, oh, question. It will not. Single link, I've tried to draw an example where single link would cluster this. Density-based clustering should not. It should give me the 2 red clusters, and then all these other points will be, they might be in one cluster or the other. Actually, some of these might be contained, but not, but all other of them will not necessarily be assigned to a cluster. I might say those are outlier points. Okay. Okay, so the algorithm is going to be phases, and it's not going to iterate over all the data points a bunch of times. Okay, and so, okay, so it's first for all x in x, find the number of points in ball of radius r at point x, okay? And if this number of points is greater than tau, then I say x is a core point. Okay, so I basically want to look at these points, and if I put the ball around them, there are going to be a lot of other points nearby. But if I compute it around this point, disappeared, okay, and I look at a ball of radius r here, and I only see kind of 4 points if 4 is less than, say, 10, and tau is, let's say, tau is equal to 10, then this is not going to be a dense point, where all these will be dense. These will be core points. Okay? Okay, 2, I'm gonna build a graph on the core points to also neighbors of radius r. Okay, well, I'll draw a more careful, smaller example on the next slide, but kind of these points should all be connected, and it should be connected to maybe even some of these points out here. These will all be connected to each other, and then maybe some of the points in the thread will be connected, but not all of them. And because these are not core points, so points that are in the neighborhood of a core point get connected in this graph. But if it's not a core point, then I don't build its neighborhood. Okay. Okay, and then 3, I'm going to say the clusters are the connected components of the graph. Okay, so these are all connected to each other, and these are all connected. Again, a connected component of a graph, two vertices or points are on the same connected component. If I can walk from one to the other ones by a series of edges here, but I cannot get from these points in the top dense cluster of 4 points to points in the bottom set of dense of the dense core points. The graph does not make it through this not dense region. Okay, and this is the algorithm. Anything else, I would say, is kind of like an outlier under this model. It's not dense enough for me to count it as one of the points I think is interesting in a dense region. And so I'm not going to put those in any cluster. Maybe I put all the outliers into an extra cluster. Okay, this is the DBScan algorithm. Okay, and okay, so how long does it take to run the DBScan algorithm? What's the runtime of this algorithm? And actually, if you look up the paper, the original DBScan paper, this was a was a controversy about 5 or 10 years ago of the paper claimed one runtime, and a friend of mine wrote a paper that said, nope, it takes longer than that, but here's an approximate version that fixes it to make it fast again. And then there was a response paper and then a follow-up paper. But okay, well, let's talk through, well, what do we think the runtime of this is? What's the runtime of the first step? Okay, and let's assume we have a fast way to find the neighborhoods. Okay, right? So where I'm willing to say that I can quickly return the number of points in the neighborhood of a ball. Maybe not constant time. Let's say, like, I'm in 2 dimensions, so I can do in logarithmic time. You know, and in high dimensions, I can use locality sensitive hashing, or I can use kind of one of these hierarchical, navigable, small world graph nearest neighbors searching strategies to find the number of nearest neighbors and measure the distance of all the points in a ball. Okay, so let's assume I can do this quickly, maybe logarithmic time, maybe n to the 1/7, something that's pretty fast for each point. Okay, so the runtime here is going to be basically n, well, let's say log n. Let's be generous here. Okay, this is not. So for each point, I can build a data structure that maybe takes near linear time, or maybe the log is some small polynomial. And then for each data point, I can query the size of its neighborhood, assign every point as being either a core point if it's dense, or not a core point if it's not dense, right? So this uses this kind of nearest neighbor algorithms that we talked about for over the last couple of weeks. Okay, that's fine. Okay, this part is hopefully is not controversial. Maybe, okay, wait, I need to build a graph here. Okay, I can build a graph now on these points, right? For every point in the neighborhood, I add an edge to keep track of the graph. Wait, so how big should the graph be? How big can the graph be? Set of all neighbors. So how many neighbors could I have among, in this example, let's say I've got 1 million points, and there are basically 45% are in this cluster, 45% are here, and 10% make up a thin string. Roughly how many points are in each cluster? 45%. And how many edges roughly are in? How many edges can you have in a complete graph? Who's had a class where they studied graphs before?
N squared.
Yeah, you can have roughly n squared edges in a complete graph, right? So if this really is dense and has a constant fraction of the points in it, 45%, I'm going to have, okay, roughly 0.45 times n squared, which is roughly n squared. Maybe 1/4 n squared, but if n is 1 million, that's a lot. This graph could be really big. Okay, so maybe this wasn't right. I just needed the number of points here, which would be okay to do efficiently. But to build a graph, I needed all the neighborhoods to build in the graph. Okay, so so this step might be n squared time step. So if I'm not careful, this is n squared time to build the neighborhood graph in case it's really dense. And the whole point is to find really dense clusters. They might have n squared edges in them. Okay, so there are some arguments that maybe I don't actually need the whole graph. I just need the connected components. So once something's in the connected component, I don't need to add the extra edges. Okay, then I need to be careful in retrieving the neighborhood graph, making sure that if I pull all the neighborhoods in and there are n neighbors, I don't need to report them all. So it's a little tricky. So I think the answer is, if you want to run this algorithm exactly, it's still n squared time. In practice, you can run it if the number of neighbors is often near a constant or a logarithmic, then it's roughly n log n. to do this and check the connected components. The connected components of a graph, if you've ever used the union find data structure, who's heard of the union find data structure? Who's taken a good algorithms class? Yeah. Union find data structure takes time O of n alpha n. Okay, and that's not linear, but alpha is basically the inverse Ackermann's function, which is this incredibly slow growing function where for the number of atoms in the universe, alpha n is like 4 or 5, right? So, okay, so this step is pretty easy once you have a graph. Okay, so, but in practice, this will run closer to n log n, or depending on how long it takes to run this step, if you have to use LSH, it's something like n to the 8/7, which is not too much bigger than n. Okay, and then you have to be a little bit careful in building the graph. Okay, does that make sense? Any questions about what the runtime is? All right, okay, so this is generally much faster. It works similar to the single link algorithms, except it doesn't, you intentionally will not capture these thin bridges here. Okay, let me kind of work through a little bit smaller example just to be clear how this would work. Okay, so I'm going to have a radius of size r, and I can think of drawing circles around. Doing a good job. It fits. Circles, if it's around one, it should be around the other point, but say these are around each other. And so, okay. So I'm going to say that this is roughly the radius. Okay, let's go label that I want the threshold for the density. Let's make this 3. Okay, so a point needs to have 3 points in its neighborhood, and I did a horrible job of drawing this, but that should be. So I want to say that these are going to be the core points because they should each have 3 points in their neighborhood. If I drew the circles right, including including themselves, okay, where these 2 points are not core, and this point is not a core point. Okay, now I'm going to draw the edges. These points will be connected to each other. These points will all be connected to each other. Maybe, or maybe that last edge does not exist. So I just have these 5 edges here, but not the one across those 2. And I also get an edge here, even though this orange one right here is not a core point, but it's within a radius of one of the core points, so it gets pulled into this cluster. These 2 points are not core points and not close to any core points, so they, even though they're next to each other, they're not part of a cluster. It's not dense enough to carry. Okay, and then ultimately, these are I have 2 clusters. This is cluster 1. This is cluster 2. And these points, I would say, are outliers in terms of this density. So this would be a little bit more detailed running of the DBScan algorithm. Okay. Any more questions on how this would work? Great. Okay, so there's one important question which you will have to answer on your homework. And I'm going to try and give you an answer without giving you the answer to your homework, okay, which is not out yet. how many clusters should I have? Okay, so with DBScan, this depended on these parameters r and tau, right? Where this was the radius and this was the threshold, and then the outcome of the algorithm was some number of clusters. Okay, for the hierarchical agglomerate with the single or complete link, you're also implicitly, you often think of a threshold for the single link. This threshold is the min distance between points in kind of diff, so clusters. And for, remember, if I had kind of these two moons, I could draw a radius around all the points. And if this was my radius of threshold, I know if I stop running the single link at this threshold, then I know that there are no 2 points between the clusters that are closer than this threshold. And for the complete oh gosh, I need to turn AI off this thing. Complete link. It's going to be the max distance between points in a cluster. So I have two. In fact, I may have clusters that overlap within each other in some way. Right, these balls around the cluster, but I know that there's this max distance between any 2 points, that I know all the points that have this diameter inside the cluster. Okay, so this is kind of an interpretation of what the stopping condition would mean. Okay, but what if you're not given that stopping condition? What if you're not given this radius or the threshold or kind of the threshold for these here? How do I choose that threshold? Right, you're just told, you know, if you're working someplace and they say, here's some data, go cluster the data. Even they give you a distance. We think this is a good way to compute the distance between our customers. Okay, here's a list of customers, go cluster them. Okay, what should you do? Yep. Oh, great. I love this answer. All right, so plug in values and look at clusters. Okay, what? Great, I like this. Can you say a little bit more what you're thinking? What would you mean look at the clusters? What would to see if they're separated? What if they're customers with 20 attributes and I'm given a distance function and it's really a function? I put two things in and it outputs a number. We'll have a way to look at them in 2 dimensions later in the semester. Okay, but what other ways can I kind of think of looking at them? Yeah. Okay, so I can compute things about inside the set variance versus outside the set variance using my distance, right? The variance, and if I have Euclidean distance, I can compute a variance. If I don't, I need to compute a mean in order to compute a variance, but I can look at the distribution of pairwise distances at least, inside versus across clusters, right? Yeah, so this is pretty good, but it gives me like these numbers, right? And I may not know if I give you a distance and then I calculate these numbers, how would I know if it was big or not big? Is 17 a big plus number inside or in between? You know, inside a cluster, is 17 a big variance number? Yeah. So I would, well, one thing I would do, I mean, there are methods that kind of do this. One is to kind of look at kind of sample data. Okay, I can take two data points from the same cluster and say, do these seem similar to me? Does that make sense? Right? Or two things in different clusters and say, does it make sense that these should be in the same cluster or not? And in this case, if they're from different clusters, they should be in different ones. So I can look at some sample data and check if it makes sense, right? This would be a sanity check. Okay, so just kind of look at sample data, see, does that make sense or does it not make sense? Okay. The other thing is something like compute some sort of value of how good the clustering is. Okay, and I want kind of the number of clusters, and I want something like the kind of compactness of the clusters. And if I sometimes you'll have something that as you increase the number of clusters, some quantity will kind of go down as I increase the number of clusters. For instance, I guess here we have the compactness is going down, but you may have something like the thresholds between the clustering is going up. But in this case, you often think of this as going down. And what happens is you get kind of this nice compactification, and then it's not getting any more and more compact anymore, and it kind of levels off. You calculate some statistic about the clusters, and it typically gets better as you get more clusters, or worse as you get more clusters. But there tends to be a steep drop, and then it sort of levels off after a while. And so what people think of this is that there's kind of this kind of hand at the end here, and that this is your arm. Okay, and then this is the rest of your body, and you're smiling because you're doing some data science. And there's a spot called the elbow. Okay, and you usually plot some characteristic about something. And when it starts to bend, you're starting to level off. You're adding more clusters, but you're not getting a lot of improvement. This is the elbow, and you say, aha, this is the spot. This is the number of clusters I want to use, right where this starts to level out. And where is that? Is the elbow here? Is it here? I don't know. I'm not like a medical doctor. So you can tell by my illustrations, but that's okay, right? If you pick 7 clusters or 8 clusters, it probably didn't matter too much. But so you kind of want to look at it and plot various things and see when is it leveling off? When am I not getting a lot of gain by having more clusters? Or if I merge them, I'd start to get worse scores than I did before. Look for these big changes in some threshold you're measuring and pick the number of clusters is there. This, I think, is generally the right way of thinking about it. There are statistical models you can use, but then you need to assume that about your data, and it gets into a whole different sort of mess. Okay, great. Well, we'll stop here, and I will see you guys in a week.